Okay, when we're doing linear regression, one of the things we really want to do is to make a model that will help predict future results. So if we think about what we do in introductory stats and how it affects regression, or even what you do in the regression class, what we do is we make our model. So there's an intercept and a slope. I'm using betas here because we're thinking mathematically. And we set up a null and an alternate hypothesis, just like you did in intro stats. So the null hypothesis is that the slope is 0, so that there's no measurable relationship between the two variables. The alternate hypothesis is that there is some sort of relationship, so the slope is going up or down. Now, when we have really large sample sizes, every single test is significant. So here is literally the same model. Just a question of how much data we made in it. And what happens is in the n equals 30 model, the p-value for that slope is a 0.594, which is totally not significant. But if we, use the same model and we generate 1,000 points, that same model now gets a significant p-value, even though the model's not any better than it was before. Now, we use this in introductory stats to talk about getting sufficient sample size that we can make conclusions. But in data science, our sample sizes are so large that the slope test starts to become meaningless. So what we say instead is that rather than thinking about statistical significance as this kind of magic bar, we instead think of it as just a first set of criteria. So if there's not a statistical significance, then we don't even want to think about it anymore. But if it is, then we think about things like effect size, correlation coefficient, which we call R squared, which we talked about last time, or a measure of prediction error. And I'm going to talk about one of those today, which is RMSE. So RMSE stands for root mean squared error. And the formula for it is right here. Again, in data science, we don't calculate it by hand. But what it is you take each point and you see how far away it is from its predicted value. Take that difference, you square it. So we have a squared error. Then we add them all up and divide by how many there are. That's a mean squared error. And then we take the square root of it to get back to the units that we started with. So in this case, when we compare our n equals 30 model to our n equals 1,000 model, we can now see that the RMSE is actually pretty similar between the two models. It is a little bit smaller, and that has to do with the fact that outliers are less likely to be influential. But this isn't actually a huge, big difference. Now, root mean squared error, unlike things like p-value or R squared, are different for every problem that you do. So you can't really just say, oh, if the number is less than 5, that's good, and if it's bigger than 10, it's bad. Instead, what you would use is we use RMSE to compare different models to see how they relate. And you might even say, in general, the one with the smaller root mean squared error is going to be a better model. Although even that's a little bit oversimplifying. So in general, the idea is that we fit models to a sample, but we want to make predictions about the population. Now, sample and population were probably in chapter 1 of your initial intro stat course, but the idea that the population is everybody we're interested in, including ones that don't exist yet. Maybe we're interested in future data. But the sample is the subset for whom we have data. Usually we assume this is a good random sample, but sometimes it's not, and we do the best we can with that. So we want to make the model to make predictions for new observations rather than trying to overfit it to the existing data that we have, because the sample may not be predictive of the population. So if we have a model like this where we fit a line, it's easy to see that this is a pretty good model and the dots are pretty close to the blue line. But if we add new data, we can see that the data doesn't change very much. It typically will be higher because this data is different, so it won't be exactly as good. But we can see that it actually works pretty well. On the other hand, if a model overfits, let's say we have 2 outliers in our data, and now our RMSE is way worse, and when we get our new data, it's even more worse. So this idea of overfitting the sample is really important to us. So one method we're going to use to account for that is called KFold Crossvalidation. And the idea is it's going to look for how influential individual points or subsets are in order to see how responsive or how susceptible our data set is to outliers. So a fold is, if you think of a piece of paper and we fold it into pieces, that makes subsets. So the fold just means subgroups of our data, but the idea is that every data point is put into one of them. So we divide the data set into these folds, and then cross-validation means that you take one of those data folds out and you fit your model without it, and then we see how important that data set is. So when we add our data back in, we get the root mean squared error of that using model 1 of that subset to predict group 1, which was the one that was left out of it. We then repeat that over and over again. And again, in an algebraic sense, this would be a really annoying thing to do, but with computer technology and with things like RStudio, we actually have commands that'll do this for us automatically. So the idea is in KFold validation, we're actually calculating K different models, each leaving out one subset of the data, and then we see how well that data set works against the others. And we keep doing this over and over again, and then we calculate a cross-validation term, which is an average of those. So this CV is our cross-validation average, and that's just the average of our data points. We can then think about a penalty that we can build into our model that penalizes this overfit. So for instance, in this penalized model, instead of using root mean squared error, we calculate the cross-validated root mean squared error, which adds in the penalty for that. And so now when we're comparing our different models, we can imagine this penalty term will help us not pick the overfit model. Again, mathematically, arithmetically, this is a giant pain in the butt, but with computers, we can do this over and over again lots of times. So we now add in this error and we see which model can now be the best. So it takes into account the regular error, but it also takes into this cross-validation, which is how susceptible our data is to outliers. And the idea is that with this cross-validation, the model is more likely to give us a term and values that will be useful for the future. So in our data set, you can see the lines are pretty actually close because we don't have a lot of error. But when we have this slightly different model, when we get our new data, it actually does give us a slightly different penalty term. I'm sorry, a slightly different root mean squared error. So this idea of generating these multiple models and then picking the best one, that's what we're really going to be doing for the whole rest of the semester. But again, it's not that we're going to be calculating these big algebra formulas. We're just going to set up some parameters and have R do it for us, and then select from the different models as we get there. This idea of cross-validating, of using some data as imaginary future data so that we can make better models, is going to be important.